It is not the quantity of water applied to a crop, it is the quantity of intelligence applied which determines the result. There is more due to intelligence than water in every case. This quote by Alfred Deakin signifies the need for rational use of water in agriculture, which is the largest user of fresh water that withdraws 70% of water from rivers and aquifers. And by 2050, we need to increase the agricultural output by as much as 70% to feed over 9 billion people. So what does this mean for our water resources? It means that evapotranspiration from global agricultural land could double if the current trends of food consumption and current practices of crop production continue. The relation between evapotranspiration and agricultural output is commonly expressed by the term water use efficiency. In this video lecture, I would like to explain the concept of water use efficiency and its related terms, and to relate crop yield to evapotranspiration, and in the end suggest measures to improve water use efficiency in dryland farming. Against a background of increasing population and climate change, we need eco-efficient approaches for rational utilization of the diminishing resources like water. Eco-efficiency is about achieving more with less, both in terms of quantity and quality. So eco-efficiency seeks to improve the sustainability of high input production systems such as irrigated lowlands and the productivity of low input production systems such as rain-fed areas or drylands. In arid areas, the water is always scarce. So to realize the full benefits of other precious inputs such as seed, labor, capital, fertilizers, etc., there is a dire need to improve water productivity. Water use efficiency relates agricultural production to water use. Originally, crop physiologists defined water use efficiency as the amount of carbon assimilated per unit of transpiration, or the amount of yield per unit of transpiration, also called as transpiration efficiency. And later they related to the amount of biomass or marketable yield per unit of evapotranspiration. Total above ground biomass is considered because of the difficulties associated with extraction of roots. Water use efficiency based on transpiration, also called as the transpiration efficiency, is an indicator of plant performance, whereas water use efficiency based on evapotranspiration is an indicator of field crop performance. The transpiration efficiency can be studied in container in which root biomass can be extracted and evaporation can be prevented. At field scale, the denominator evapotranspiration can be measured from P, that is precipitation, I, that is irrigation, G, that is net groundwater flow, Q, that is run on or run off, and delta S, that is change in soil water content within the root zone. All of these parameters are measured in millimeters of water. However, evapotranspiration of crops is more easily determined from the measured climatic variables and the predetermined crop coefficients. For most crops, only the economic part or marketable yield is of interest for researchers. Therefore, uh, water use efficiency can be considered as economic yield per unit of evapotranspiration. First equation shows the transpiration efficiency. Gregory in 1988 proposed an expansion of the equation 1 in the form of equation 2. And since in semi-arid conditions, runoff, drainage, and interception of rainfall by crop canopies are also substantial components of water balance, Gregory suggested the third equation. Equation 1 and 2 are particularly useful because they indicate the possibilities for improving water use efficiency. That is, number 1, by increasing the numerator or transpiration efficiency, and number 2, by increasing transpiration proportionally more than the other forms of water losses. Since it is difficult to measure evaporation and transpiration separately, therefore, these are usually expressed in combined form as ET or evapotranspiration. But strictly speaking, evaporation is the wasteful part. It is considered as the water loss from the soil surface or from soil and plant surfaces or plant canopies. The evaporation from plant canopies can be considerable during rainy seasons. But transpiration is strictly speaking the loss of water from the substomatal cavities or through stomata. So evaporative losses are high in bare soil or fallow land during early part of growth when leaf area index is low because ground cover is incomplete, and therefore it is important crop management practice to increase ground cover as early as possible. But there is also a risk that too much early vigorous growth can extract the available soil water rapidly, causing terminal drought stress around flowering or grain filling. Transpiration is the loss of water from living plants. About 90% of transpiration is through stomata. The openings are pores in the leaf epidermis. While under dryland conditions, sometimes cuticular transpiration also becomes important. The legendary crop modeler C.T. David related biomass to transpiration for high radiation environments with the equation dm is equal to mt divided by E naught, where dm is dry matter, m is crop coefficient, and E naught is mean daily pan evaporation. Since yield is a product of dry matter and harvest index, y over hi can be substituted for dry matter. Hi or harvest index is the ratio of economic yield to total above ground biomass or biological yield. M or crop coefficient varies with C3 and C4 mode of photosynthesis, and its value is higher for C4 than C3 plants. E naught can be substituted for vapor pressure deficit, that is the difference between saturated vapor pressure of air at a given temperature and the actual vapor pressure at that temperature. Vapor pressure deficit is mainly affected by weather variables, but farmers can manipulate it through adjusting planting dates. In dryland conditions, transpiration mainly depends on the amount of precipitation, runoff, and the amount of water stored in the root zone, as well as the atmospheric evaporative demand. Crop characteristics such as leaf area index, root density, root biomass also highly correlate to the amount of transpiration. Although transpiration has a linear relationship with crop yield, but under dryland conditions, this relation may become non-linear due to water scarcity and low yield. When the yields levels are less than 50% of the potential yield, then the relation between transpiration and yield may no longer be linear. This relationship also becomes non-linear in case of sparse canopied crops and low harvest index. Harvest index is highly variable generally in dryland conditions. Water use efficiency and yield can be improved by better agronomy or better management practices for soil, water, and crops, and by better breeding. Water management practices for improving water use efficiency and yield in dryland areas include supplemental irrigation, small and timely irrigation at the time of crop need, deficit irrigation, low pressure sprinkler irrigation system, subsurface drip irrigation, and water harvesting for maximum water infiltration and water storage in the root zone. However, farmers must not be tempted to overexploit the groundwater in order to supply the supplemental irrigation. Soil management practices for improving water use efficiency should aim at improving water filtration by deep plowing before the onset of rainfall and shallow plowing after the rainfall to prevent evaporative losses and to improve infiltration. The soil management programs should invest in soil fertility, maintenance, and prevent soil degradation to avoid the loss of organic matter, nutrients, uh, poor rainfall infiltration, and to avoid poor root establishment. When we talk about crop management practices or better agronomy in arid areas, optimum or balanced fertilization is the key. When the yield levels are too low, normally there are causes other than water, such as poor soil fertility. So, balanced fertilization is the key for improving water use efficiency because nitrogen application improves leaf area index and leaf area duration, which ultimately improves the ratio of transpiration to evapotranspiration. Phosphorus application improves rooting capacity of the soil and available water. And potash application improves the uptake and transport of water to reduce water stress, particularly in sandy soils and at critical stages of crop growth. Another important strategy is adjusting planting time and fertilizer rates to available water supplies because there is a positive interaction between water and nitrogen availability. Water availability improves nitrogen use efficiency as well as water use efficiency. In order to prevent nitrate leaching, slow or controlled release fertilizers can be used where available. Fallowing also improves the amount of stored water in root zone, but care must be taken that the fallow land is free of weeds. Mulching is also a useful strategy which is highly recommended, but due to the limited crop residues available in arid areas or low ground cover, usually the tillage mulching or dust mulching is useful. Improved seed varieties, fertilizers, pesticides, energy for tillage are also crucial for increasing crop yield and realizing full yield potential. Planting patterns, plant populations can be adjusted to match the available water supply, and we have to reduce the yield reducing factors such as weed, diseases, and insects as we do in the irrigator systems. And the last but not least is selection of multiple cropping to avoid complete crop. Efficient use of water is seldom a goal of farmers. In irrigated areas, normally it is about maximizing profit, while in dry lands or arid areas, it is about risk management. There are some limitations when we use the term water use efficiency as well. For example, some researchers have pointed out that water use efficiency is actually an index and not an efficiency because there is a theoretical limit for yield. And the typical term water use efficiency, which relates yield to transpiration or evapotranspiration, does not include all the agricultural benefits like economic or social or environmental benefits such as groundwater recharge. Therefore, the term water productivity is being increasingly used to express the total agricultural benefits, economic, social, and environmental, that we obtain by efficient utilization of the available water.